Good afternoon, ladies and gentlemen. Welcome to the Hong Kong Science Museum, attending the United College Distinguished Visiting Scholar Lecture in 2016 to 17.
We are the master of ceremony of today's lecture. I'm Angel Chen, Journalism and Communication Year 3 student.
I am Sam a Year 2 student also majoring in Journalism and Communication. The United College Distinguished Visiting Scholar Scheme is made possible by the generous support of the college's endowment fund. Under this scheme, United College is able to invite world-renowned scholars to Hong Kong to give public lectures and to meet staff and students of the college and the Chinese University of Hong Kong.
We would like to express our gratitude to the Philomathia Foundation, which supported the Distinguished Visiting Scholar Lecture in this year.
2016 is a special year for United College, for it celebrates its 60th anniversary. The college has much privilege to have invited Professor Stephen Chu from Stanford University as our Distinguished Visiting Scholar in 2016 to 17.
Without further ado, I would like to turn the floor to the moderator of today's lecture, Professor Steve Xie. Professor Xie is a professor in the Department of Chemistry of the Chinese University of Hong Kong. May I now call upon Professor Xie to introduce Professor Stephen Chu and the topic of this afternoon. Professor Xie, please.
The United College is one of the first three original colleges at the Chinese University of Hong Kong. Our college was founded in 1956, so this is our 60th anniversary. In fact, this is a very special year for us, and for this special occasion, we are very lucky to have a very special visitor to share and celebrate this occasion with us. Professor Stephen Chu. He is the William R. Kenan Jr. Professor of Physics and also Professor of Molecular and Cellular Physiology at Stanford University in the USA. He was born in St. Louis, Missouri in the US, and with actually ancestry from Jiangsu, China. He got his bachelor's degree in physics and mathematics from the University of Rochester. And then he went to the University of California at Berkeley to get his PhD in physics in 1976. And his graduate study was actually sponsored by a very prestigious fellowship by the National Science Foundation of the USA. He has many honorary degrees from different places, and he is also a member of many international and national research academies. Out of so many awards that he has received, I think one stands out. In 1997, he was a recipient for the Nobel Prize of Physics for his work on using laser to cool, to slow down, and trap atoms. Very interesting enough, many of his family members are also very impressive, with multiple doctorate degrees and professorships and also professional positions. I think one important stage for Professor Chu's career was that he became the 12th US Secretary of Energy in 2009 under the administration of President Barack Obama. He was the first scientist to take up this position as the Secretary of Energy. And I dare say he was probably the first Secretary of Energy who actually understood the principle of the energy applications. And under his leadership, the Department of Energy was able to recruit many outstanding scientists and engineers, and we can actually now see some of the great work being carried out by these scientists and engineers. And Professor Chu is going to give us two talks this week. The first talk will be here today, and the next one will be on Thursday on the CUHK campus. The title of the talk today is A Random Walk in Science. We don't always advance science with a clear vision, but Professor Chu is going to tell us today how it has worked out for him despite the uncertainty. Without further ado, let's welcome Professor Chu.
I want to talk about people's milestones in their career. You're all young students, and so you're not actually so sensitive to this, but when you become an undergraduate student and then a graduate student, the first milestone in your career is you write a paper, and you submit the paper, and it gets accepted. And so that's a very big deal. And the next thing that could happen is you advance, is you're invited to give a talk at a conference. So that's called invited talk, first invited talk. Time is going by, your scientific standing is increasing. And then there are special talks at a conference. They're called plenary talks. And you were asked to give a plenary talk. This is very good. But there's grade inflation, so they have to think of something higher than a plenary talk. So they call it a keynote talk. Now, there's a few keynote talks, and that's great. Notice you're reaching the peak of your career. Now, after that, you give your first after-dinner talk. This is going downhill. And then in your after-dinner talks, you begin to talk about other people's work at these talks, and then you begin to mess up the description of other people's work. So it's going closer and closer to this. And then you become a bureaucrat who speaks at ceremonial occasions. Now you notice on the y-axis, scientific standing, there's no units. Well, there is one that's important, and that's where is zero. Zero is at the bottom. And afterwards, you can go further than that. You can begin to talk about the good old days, and you mess up the history. So this talk is about the good old days and about my scientific life, and it may not be all accurate. All right. So it was mentioned I came from a very distinguished family, both my father's side and my mother's side. This is a picture of my grandfather and my granduncle. My grandfather is on the left. This is after they came to America. His name is Xiuten Li. He got a PhD from Cornell University, and he became a faculty member there, and they became the dean, and they became the president of the university by the time he was 32 years old. This is a little early. His brother was equally impressive. He got a PhD in physics at the University of Paris, became Minister of Education of China at 41, but only 1 year, and he became head of the Academia Sinica at age 42, and he did many other things, was a founding member of UNESCO and other things. So this is a very scary family. Now, my mother and my grandfather, her father grew up in Tianjin. That's what my mother looked like when she was a young lady. Now, a little bit on my father's side. That's my father. He was, both my mother and father came to the United States to work on a PhD at MIT during World War II. And he got his PhD in chemical engineering. Well, they're now passed away, but when he was alive, he kept on reminding me that he got his PhD in 2 years. And why did it take me 6? So in any case, he became a professor first at St. Louis University in Washington, in the state of Missouri, Washington University in St. Louis, and that's where I was born. But then later, he got a very nice full professor job at then a very good school in chemical engineering, Brooklyn Polytechnic. So they moved to Long Island, New York, and that's where I grew up. And this is my mother and father on their wedding day. The woman on my father's right is his oldest sister. She got a PhD in chemistry and was a professor at Tsinghua University in the 30s, okay? Now, you probably noticed that my father and mother are, reasonably attractive looking. That's another picture in their wedding day. So how could parents like this have a baby like that? That was me. And a bad hair day. I was a little chubby. Even when I was in grade school, I was still a little chubby. But then I eventually grew out of it in high school. All right. So I was not only ugly, I was the academic black sheep of the family. Not only, it was mentioned, my older brother, he got the highest cumulative average in the history of the high school. Not that year, just in the history. And he went to Princeton as an undergraduate. He got a PhD in physics. And when me, the middle brother, and then the younger brother were growing up, everybody told us, oh, you know, you're going to be just as good as Gilbert. That's the name of my older brother. But this was too much pressure. So for 3 months, I dropped out of high school in the 9th grade. And I finally went back and took the final exams. By the way, I don't recommend you drop out of high school. But in any case, and then my older brother went on to become a postdoc in physics, but later he got interested in medicine and he got an MD PhD at Harvard and MIT joint program. Meanwhile, my younger brother was even more rebellious than me. I only dropped out for 3 months and finally went back to school because I didn't want to compete with my older brother. But then I went to the University of Rochester, and when the first semester, I started to do very well. And then my parents talked to my younger brother and said, oh, you know, Gilbert's doing very well, Stephen's now doing very well, what about you? And he didn't like that. So he dropped out of high school at the end of his junior year and never went back and bummed around. And finally, after a while, he said, well, I should go to college. So without the blessing of the parents, the high school, he talked his way into UCLA. He got a PhD there at the age of 22. And then he went on to get 2 law degrees at Harvard. Okay, this is a very scary family. I'm the only person with only 1 advanced degree. I was the first male child in the family not to go to Princeton or Harvard, in the extended family. Okay. All right, so that's the sad story of my personal life and feeling very inferior. So let me tell you how I learned to do research. And that really began when I was in graduate school at University of California. And there are many secrets that one may have, but I had just one simple secret. I had a great PhD mentor. My advisor was a wonderful, wonderful, brilliant physicist, but he was also a wonderful person. And all the students he had adored him, and he was a wonderful lecturer. So when he gave lectures, he was famous, not only in the physics department, but throughout the science departments at Berkeley. This is a picture of my advisor with my mother. This happens to be at the Nobel Prize ceremony, and you can't tell what they're saying, so I'm just making this up. But my mother might have been complaining to me and would say, he never listened to me. How did you get him to listen? How did you get him to listen to you? Of which Gene Cummins, my advisor, is very polite, so he wouldn't say anything, but he probably thought, what makes you think he listened to me? In any case, he was a wonderful person. This is where I went to school. The time I went to school, 1970 to 1976, there were 9 active Nobel laureates in the physics and chemistry department at the time. But it's more than that. It's more than a bunch of people with big names. There was lots of young professors who were terrific. And the students were very, very good. Just to give you an example, when I was a student at Berkeley during that time, that's physics in LeConte Hall, these are some of the classmates who got Nobel Prizes later on. That's pretty good. So those people were all students the time I was a student. Anyway, so let me tell you about my graduate career and what I did in research. Well, I worked for Gene, and the first thing he gave me was a theoretical problem. I was a math major and a physics major, and he thought maybe I wanted to be a theoretical physicist. Now, in those days, no one encouraged you to be a theoretical physicist, but for some reason, it was okay. So he gave me this problem on how binary stars formed. I worked on it for 3 months, not making much progress. And I kept on going into the laboratory and just playing with my hands building things. So finally I went to him and said, Gene, I don't want to be a theoretical physicist. I want to be an experimental physicist. So he said, okay. So fine. I get an incomplete my first project. I'm giving myself grades. The next thing I did was look at radioactive decay as a test for a theory in what are called weak interactions, or the weak nuclear forces. So it was a test of a theory, and I worked on it for maybe 3/4 of a year. And there's one night we had this run at an accelerator. It didn't look like it was going to work that well. And my advisor looks at me and says, maybe we should do something else. So I got another incomplete. Okay. So then he said, why don't we do a test that tests the theory of electricity and magnetism, which was written down in around 1864, and it was unified with the special theory of relativity in the 1930s and 40s. And then people who finally did the unification got a Nobel Prize for that as well. And so it's a very, very important theory. So why not do an experiment on that? I worked on it for about a year, got something more interesting, so I get another incomplete. Okay, I'm a graduate student, 3 years, 3 incompletes. This is not an auspicious beginning. All right, so what did I end up doing? There was a paper that was published that proposed a way to do an experiment that could test not only the unification of electricity, magnetism, and special relativity, it could unify all those things with those weak nuclear forces, which I'd been doing an experiment on. My advisor was an expert in that area, and we read this paper and said, this is what we want to do, so we dropped everything else. So this is what I worked on. That was me when I was kind of young. We were all young ones. Anyway, that was me adjusting something in that box you see open up was a laser that I had built and designed. And I don't have a pointer. Oh, yes, I do have a pointer. And my first paper was actually how to make this little thing in here. It wasn't a science paper. It was a little gadget paper. Anyway, so that's what I did. So now, after a graduate student, it was nearly 6 years, my father telling me what's going on here. And I went to my mentor and said, you know, Gene, I've suffered enough. I'll make you a deal. If you let me get a PhD, I'll stay and finish the experiment, because it was harder than I thought. So that's what happened. By the way, that's what I looked like when I was a graduate student. And so this test of the unification of electromagnetic and weak interactions. So let me just pause here. So actually, for some reason, I didn't look like what I looked like was a baby. I don't know what happened. So the test of unification of electromagnetic and weak interactions, that took 5.5 years. It was barely a result. It was not so good. And not only that, but you know, the world was looking at this experiment, but just before we were going to publish it, the SLAC accelerator at Stanford did a high-energy experiment that was very, very good and just took all the thunder out of our experiment completely. And it was a much better experiment anyway. So I give myself a C for that one. All right, this is really not so good. Nevertheless, it was very strange, because the spring of 1978, as we were finishing the first version of this experiment, the physics department asked me to apply for an assistant professor job. So I gave a talk in front of 400 people. And then later they said, okay, we're going to hire you if you want the job. So I said, that's great. So I took the job. I'd only published 1 scientific paper in that time, and 2 device papers. So it was very weird. I couldn't understand why. Then they said, and it's not a job to work for my mentor, it's a job as an independent researcher. They gave me some setup money. I said, I took the position. I promptly spent all the money in those days. It was only $25,000. I built 2 more commercial lasers to build a big laser system that can even do the job better, which was actually not the right thing to do. So that's what I did. But Berkeley also said something else very strange. They said, since you spent 8 years at Berkeley, we want to have you as a faculty member. You can start teaching immediately and start your research group immediately, or you can go away for 2 years, anywhere that will take you. We won't pay for that, but you can go anywhere, broaden your wings, learn more different kinds of science, and come back. So I said that was a really good deal. I took the job. I went to Bell Laboratories. So this is the laser system that I built. While I was building it, the last part of my last year, with the money they gave me for being a faculty member, what was going to be my first graduate student was a beginning graduate student, and so we built this thing, and it worked, and she used this laser to do her PhD thesis. Now, I should say that Persis Drell became a good eminent scientist in her own right, member of the National Academy of Sciences, became director of SLAC, and is now the dean of the engineering school at Stanford. So now, when I left Jean's group, when I became a assistant professor, I didn't think I knew much physics, but I did know how to make lasers and machine. Anyway, so one of the lessons I learned at Berkeley from other professors, including many Nobel laureates, is that if you build a new instrument, so I built 2 lasers, they were very successful. That first laser was so successful that the physics department actually built 5 others, just like it, just copied it. It worked much better than anything you can buy, and then the other professors in the department used that laser, the laser design. Anyway, if you build a new instrument that works better than something else, you get to do experiments that no one else can do. So I say it allows you to see with new eyes. Now, imagine you're a scientist exploring and you look under a rock, and you're the 100th person that overturns the rock and looks on it. Well, you discover something new. Not likely. You got to be really smart. If you're the first person to look under the rock, you're much better off discovering something new. And in fact, you don't even have to be smart, because you're the first person to look at it. You're the first person to look at it because you have a new instrument. And that is really what a lot of science, especially physics, has done for hundreds of years. Galileo, telescope, Leeuwenhoek, microscope, all of these things open up new vistas. So that is a good formula. So I went to Bell Laboratories. This is a picture of Bell Laboratories in New Jersey, Murray Hill. It was a wonderful laboratory. Again, lots of Nobel laureates. It turns out that 15 scientists who worked there got Nobel Prizes. But what was unusual about Bell Laboratories is they were hired when they were all very young. They weren't hired as established people. And I was hired, just finishing my postdoc, a very beginning assistant professor. Most people were hired out of graduate school or just finishing postdoc. And it was a special place. And so I wrote about it later, and I described my experience there, that I was one of roughly 24 young, brash scientists that were hired within a 2-year period. We felt like the chosen ones, with no obligation to do anything except the research we loved best. And the joy and excitement of doing science permeated the halls, and the atmosphere was so electric to abandon, I never returned to Berkeley. That's not quite true. I returned to Berkeley 26 years later. But, it was a very special place. We didn't have to worry about funding. There were very, very smart people around us. And the Bell Labs management shielded us from extraneous bureaucracy and urged us not to be satisfied by merely doing good science. And my department head told me to spend my first 6 months in the library and talk to people before deciding what to do. He also, at one period, during a merit review said, I should be not content with anything else than starting a new field. So I was very cheeky, fresh. So I said, I'd be more than happy to do that, but I needed a hint as to what new field he had in mind. So, when you start a new field, it doesn't even have a name. So in any case, what happened? So life at Bell Labs, I worked on a problem. It was, again, to test the theory. Most of my early experiments were to test someone's theory. It was a theory that was part of Phil Anderson's Nobel Prize that he got in 1990. Oops, that's a misprint. 1977, and I got to Bell Labs in 1978. And he said this one single experiment that verified this theory was it. And so I and some colleagues looked at it and said, well, that's good. We can strengthen the experiment. We can do it much better. We can do other versions and see what happens. We did it, and it turned out the experiment was wrong. That's unfortunate, and we went on to show that the system didn't even apply. Then I did an experiment with another colleague where you take an electron and its antiparticle. Every particle has an antiparticle. And instead of an electron and a proton, which is a hydrogen atom, you have an electron and its antiparticle. They go around each other, and that's called positronium. And then later with Jan Hall. And this made a big splash, but it didn't lead to any new discoveries. It's something that people were trying to do for about 20 years, not succeeding, so it was technically hard. It was a test of a fundamental theory, but the theory was right. And then after that, okay, anyway, that's what I looked like when I was doing that experiment. See, notice I'm getting older and older. And then I did other experiments. I don't want to go through all of them, but finally I started to work on whether it's possible to cool and trap atoms with light. Now, I'm not going to go into the history, but let me just tell you what cooling is. The molecules in this room are moving very fast. They're moving at the speed of supersonic jet planes. In fact, that's why speed of sound is what it is. But if you wanted to hold on to atoms with light, you had to get them very, very cold. So instead of moving at the speed of a supersonic jet plane, you actually have to get them to move as fast as my hand is moving. It's very, very slow. Okay, so imagine there's an atom here, and it's moving really fast, but you know where it's going. So you can take a laser beam, and you can shine light on it, and the light hits the atom and scatters, and every time, think of the light as little particles of light, little photons, and the atom is this big bowling ball. And so the bowling ball is rolling down, and the little ping, 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 and after tens of thousands of ping, 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 the bowling ball slows up. Okay. Now, what if the atom, and so there's a force on the atom. Now, here's a trick. We're going to put a laser beam in back of it. Now, normally you wouldn't want to do that, but there's something else that happens. This atom might be going this way, but this atom might be going that way. And you don't know which way they're going, but some are moving this way, some are moving that way. So we're going to put two laser beams, and we're going to use something called the Doppler effect. Now, a Doppler effect, I have to demonstrate the Doppler effect. I'm going to walk toward you, and as I walk toward you, my voice goes up. And I walk away from you, my voice goes down. So that's the Doppler effect, exaggerated. If you, let's see, I guess you're in Hong Kong, you don't have trains. But anyways, if you're on a train, you hear a dinging bell, and as the train is going up to this crossing, you hear ding, 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 and as it goes past the crossing, you hear ding, 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 ding. That's frequency shift because you're going fast, okay? So you have these two laser beams, but you're going to tune the light so that if I'm going towards one laser beam, I'm going to more likely to get photons hitting me and scattering and slowing me up. But I'm running away from this laser beam, so it's less likely to do that. And if the atom goes in the other direction, the opposite happens. So no matter which way the atom goes, it has tendency to slow up. The atom goes up, you have 2 more laser beams, force opposing its motion. I was really excited about this idea. And so I was doing an experiment to do this, and as I did the experiment, I went and told my boss, I was the department head at Bell Labs at the time, and I told my boss, this is an idea that once you can cool atoms, you can trap them, and it will work. And he kind of looked at me and said, well, my boss had actually shut down the work at Bell Laboratories 4 years before that, 5 years before that, because some other people had tried to do that 15 years before and didn't succeed, and after 10 years, they said, well, look, we're not making much progress, it's time to move on. And so I come along and say, well, no, I want to do it again. Yeah, right. So but he let me, and then he said, but don't try to talk the others into working with you. All right. So I didn't. After 7 months or so, it looked like it was really going to work, so I said, psst, come on, join me. It's going to work. And then 1 year after I started the experiment, only 1 year, it worked. I sat down to write the first draft of the paper, and then one of the older veterans, Art Ashton, said, you know, I think you should read this paper. It was written by these 2 people, because I think it has something to do with what you just did. I looked at it, I read it, and I said, oh, it had everything to do with what I just did. They proposed it 10 years ago. It's a little 2-page paper. But they didn't think it was important, and they didn't do anything about it. Now, one of the people, Art Shallow, was a co-inventor of the laser. He got a Nobel Prize in 1983. He didn't mention this paper that he wrote in 1975, but I did the laser cooling in 1985. Okay? So I said to him, he was the one who recruited me. In fact, both of them recruited me to go to Stanford. And I said, Art, why didn't you even mention this paper? You mentioned 25 other papers that you did, not this one. And he kind of looked at me. He's very honest and said, 1983, I didn't think it was going to be important. So this is how funny science is sometimes, even by the inventors. And Ted Hench didn't think it was important. They could have done it probably by 1980, by 1978, if they thought it was important and had the right approach. But it was good. It's very kind of them to leave something for younger people. Anyway, we call this stuff optical molasses. This is what it looked like. These are atoms coming really fast, going twice, 3 times the speed of sound out of that little nozzle. And they go into a region where there's crisscross laser beams, and they quickly cool down and go to just less than a thousandth of a degree, a few hundred millionths of a degree, millionths of a degree above absolute zero. Okay, so it was very, very cold. And then the following year, we were able to trap atoms. The following year after that, we were able to get a really good trap, and everything changed. So, okay. Now, I should say I made a mistake. The measurement we made wasn't good. It would turn out to be much colder. And then several years after that, French physicists Jean Dalibard and Claude Cohen-Denougy figured out the theory for that, and I, within a few weeks at the same time and independently, also figured out the real theory for why the atoms were so cold. And so the group that made the discovery that the atoms were colder than they should have been shared the Nobel Prize with me, and Claude Cohen-Denougy, who did the theory independently of me, also shared the Nobel Prize. If I had done a better experiment, I wouldn't have had to share it. But just seriously speaking, I'm very happy to share with these people. They remain good friends during the whole time. We were competing, but we were also friends. Anyway, so in 1987, the fall of 1987, I went to Stanford, and a beautiful place. And this is me when I just joined the faculty at Stanford, age 40. So you can tell I'm getting older. And, oh, by the way, I love to wear Mickey Mouse shirts. In fact, I was famous for wearing Mickey Mouse shirts. And And one graduate student graduated from my group, as a president, he's leaving. He gave me another Mickey Mouse shirt because the other one was wearing out. Anyway, so why are people interested in cooling and trapping atoms? You know, what good is it? Well, there's one thing I knew that was good even when I was at Bell Labs. If you get them really cold and turn off the light, they drop to the bottom of the vacuum chamber like stones. Boom, they're that cold. You know, but they're only moving this fast. So if a stone is moving this fast, it goes, but atoms do the same. If they're that slow, you can actually toss them up with light, and if they go up, turn around, do the gravity, and come back down, it turns out you can have a lot of time to make very precise measurements, and that are limited by fundamental theory called quantum mechanics. And so we made this so-called atomic fountain of atoms that go up and come back down. And this magneto-optic trap that we showed in 1987 became the dynamite workhorse of the trapping world, cooling world as well, because it works so well that it's now an undergraduate physics experiment. It's really that easy. But in those days, you know, who knew it would work so well? And anyway, so we did this. And with that atomic fountain, we then showed, and other people also showed, that you can make much better clocks, atomic clocks. And so within 7 years of this first fountain, the time standard used this fountain principle to make better atomic clocks. The atomic clocks today are so good that they have an uncertainty of 18 decimal places. Now, what does uncertainty mean? The age of the universe is 13.8 billion years old. That's a long time. Just pretend you started one of these clocks when the universe was at the time of the Big Bang. It starts ticking. You would know how old the universe is to about a half a second. Okay? Now you're probably wondering, I hope you're wondering, so who cares? Why do you care to have such a good clock? The 14 billion years, half a second? You know, my wife says I'm actually 10 minutes late for everything. In fact, it's really worse than that. I have a watch, and I set it 20 minutes faster. Because then I forget it's 20 minutes faster, so I'm only 10 minutes late. Otherwise, it'd be half an hour late. Okay, so I'll tell you why it's so important. The most precise measurements and the most precise things we know are actually measured in terms of time. The meter used to be some length on a metal bar, scratches on a metal bar. Once we had a good time standard and could measure the speed of light, we defined length as what? We defined the speed of light. It's actually defined. So-and-so meters per second. What does that mean, you define the speed of light? Because you're actually defining the meter. Because you know what fraction of a second it takes for this atomic clock, and it's how far light travels in 1 meter, by definition of the meter. So the meter is defined now in terms of a length. Okay? Now, of course, the speed of light is the speed of light, but you know, it could be meters per second, it could be feet per second, it could be miles per second. It's the speed of light. So the unit is not important. Turns out the electrical units for voltage and resistance can be defined in frequencies. Each of those things got people Nobel Prizes for discovering that you can measure the voltage as a frequency, resistance as a frequency. Okay? And there were about 10 Nobel Prizes making better atomic clocks or using better atomic clocks. So atomic clocks are a big deal, very big deal. Okay? And the most sensitive fundamental tester. So when you make a better clock, it gets people's attention. The global positioning satellite system are a bunch of satellites, and the heart of it is an atomic clock. And then these atomic clocks not only tell you what time of day it is, by triangulating on where your cell phone picks up 3 global positioning satellites, and you can now navigate around the streets of Hong Kong. You're lost. You punch in where you want to go, and out pops a little map, and on it shows where you are, and it's blinking around, and you can walk to where you want to go. That's because of atomic clocks. There are other things, basic science, the tectonic plates that shift and cause earthquakes. They're measured in terms of atomic clocks. All the data transfers around the world through the fiber optics are measured through atomic clocks. It's the atomic clocks that synchronize the packets, because you know how data is transferred. It's really a crazy way, but it worked really well. It was invented in the middle 1970s. It's like you want to get the information out of a book, and you want to give it to someone else. So what they do is they chop the book up into little pieces, maybe three slices per page, little pieces, and they send out little bits of the book over this way, and another little bit over that way, and another bit over that way. And the clocks are all keeping track of where they're sent, and they're assembled somewhere else. Why would they do that? Why would you take a book, shred it up, send it over different places, and reassemble it? It's because in the 1970s, the internet didn't work so well, and they wanted a more robust system to send information around and reassemble. It's called TCP/IP, okay? That protocol. But it depended on timekeeping. That we had. In the 1970s, we had good clocks, crystal oscillator clocks. As computers got faster, as data transfer got faster, it became more demanding, and we had to go to atomic clocks. So it's important. All right, so we can take light, and we can hold on to atoms. My colleague Art Ashkin showed that you can take light, and you can actually hold on to bacteria and things inside bacteria. So I said, that's great. You can hold on to atoms with light, you can hold on to bacteria with light. So when I got to Stanford, I said, can we hold on to a molecule, a single molecule with light? So the idea was you glue a little plastic sphere, and you can hold on to the sphere, and you stick it onto a molecule, a big molecule like DNA, and see if it works. And so when I got to Stanford, I said I didn't know any biochemistry, so I found an MD PhD student. I asked around and said, oh, you should talk to this guy, Steve Krohn. He's a very bright student. And I talked to him and told him what I wanted to do, and he says, okay, I'll teach you a little biochemistry. And so at night, he would teach me a little biochemistry, and we'd fool around, and we'd do it. And it worked. And there was an undergraduate student who did his honors thesis with me, Steve Quake, and I said, hey, got this crazy idea. Steve Krohn just showed me how to stick little spheres onto the DNA. Let's see if we can make them move around. And so here's a movie of a single molecule of DNA glued to a little polyplastic sphere, and the light is introduced into a microscope, and you move the light beam around with a little joystick, like a computer game, and the molecule moves around, okay? That was done in 1990, a long time ago. And it opened up lots of applications in biology. And through this, I started getting more and more interested in biology. And by 1995, 96, 97, most of my work was starting to shift into biology. So I was completely changing fields. We worked on, atom clocks. We worked on atom interferometers. We worked on a whole bunch of other things. But I started getting interested in biology. Okay. So that's me when I got the Nobel Prize. Now, that's at the Nobel Prize ceremony. That's me on the right, my younger brother in the middle, and my older brother on the left. And in this very distinguished family, I finally felt like I can hold my own. Okay, so anyway, so that's what we looked like then. All right, so that was 97, and I continued doing, by then, heavily into biology, and very happy doing research. But I began to get interested, not as a scientist, but interested as a citizen about climate change. I didn't know whether it was correct or not, but I began to read about it, and then began to get more concerned. I began to actually give talks on it. And in 2004, Lawrence Berkeley National Laboratory wanted a new director. The old director was my boss, who allowed me to work on laser coolant trapping. It's a very incestuous family. And he had been director for 15 years, and he wanted to step down. And I said, I'm not interested in the job. I was happy being a professor. I don't want to be a big boss. And they asked me twice, and I said no. But then he said, look, just come for an interview. If there's a 5% chance you're doing, fine. If it's less than 5%, we don't want to talk to you. You don't want to talk to us. It's wasting everybody's time. But if there's a small chance, just think about it. So I thought about it a little bit. I went for an interview, and they offered me the job. And so I said, all right. Now, why did I do this? And then I was director for nearly 5 years, and I was going to step down and go back to doing science. By this time, I was professor of physics and molecular and cell biology in Berkeley. So I did go back to Berkeley, as they said, after 26 years. But I was going to step down, and then in November of 2008, I got this strange phone call from someone from Chicago. Said, the president-elect would like you to fly to Chicago to talk to him about an important job. And I said, well, I'm not so sure. I'm very happy what I'm doing here, but I'm actually thinking of stopping being a bureaucrat. Remember, bureaucrat, you're just going negative. And I wanted to go back to being a professor because I really like doing research. I like teaching. I like training students and postdocs. So I said, but how important is this job? Secretary of Energy. So I said, maybe I should go there. So I went there and met him in some big empty room in middle November, and he goes up to me and shakes my hand and says, everybody tells me you should be the new Secretary of Energy. By the way, I didn't do any politics. I didn't campaign for him or anyone else in my life. So I stood up, shook his hand, and said, who are these future former friends of mine? That was a joke. He just ignored it. And so for the next hour we talked. He wanted to know what I thought about energy of various types and nuclear energy and how we do this and that. What are the issues? And so we just chatted. He listened. He asked questions, whatever. And I was very impressed with him. Very, very bright guy. So after this meeting, this interview, I guess it was, I flew back and I told Jean, my wife, if this guy asks me to do it, I will accept the job. And he asked me to do it a few weeks later, and I said, okay, I'll take it. So I went to the Department of Energy. Why did I do this? Why did I go to Berkeley Lab and Department of Energy? Well, Berkeley Lab was a special place. When I was a graduate student at Berkeley, I also was an employee of Berkeley Lab. And when I was a postdoc, I was also an employee of Berkeley Lab. And now I was paid by the National Science Foundation, but I still had visiting privileges, not visiting privileges. I had a little card, and I could get in, and we could buy stuff, and there's equipment places and things like that. But it was a very special place because it trained a lot of very young, good scientists. It also has lots of Nobel Prizes in its history, I think about 14, also part of Berkeley. But the amazing thing about Berkeley Lab is students, graduate students, postdocs, young scientists started a career, over 30 worked at Berkeley Lab. This is amazing. So I said, if I can be the boss of this really prestigious, good place and can convince people how exciting it would be and how important it would be to work on energy, clean energy, that could help in climate change, it would be worth it. Now, I took the job, immediately started talking to people, and starting with the professors. And there's a small group of professors, and we got together, and they said, well, we don't know that much about energy. He says, don't worry, neither do I. We're just going to teach ourselves. And so every Friday, for a couple hours, we'd meet and discuss things, and then we would have workshops and things like that, and this went on for about a year. Even though we weren't doing it in response to a call for proposals. We were just doing it. Now, it turned out to be really lucky because about a year after, there's a call for a big proposal. British Petroleum, or BP, wanted to give $500 million to fund research in biofuels. And they weren't even considering Berkeley or Berkeley Lab, but then they heard about what we were doing just by word of mouth. They thought it was going to go to Illinois or MIT or someplace. And so they invited us. They only invited people to apply. There were 6 or 7 institutions that were invited to apply, and we got in and squeaked in at the last moment because somehow they got word that a small group of scientists were thinking very hard about these problems: renewable energy, solar power, biofuels. And we got the grant, $500 million. It's nice. So we got really lucky because we were doing this even before we knew there was going to be a grant. Okay, so why, I'm going to tell you a little bit about why I was concerned about climate change. This is recent data, and this is an interesting thing. This is a cartoon of 2 satellites that go around the Earth, and if they're, in this cartoon you see in the upper right-hand corner is a cartoon of Greenland with a big ice sheet. But if the ice in Greenland melts, then the mass over Greenland is a little less, and it changes the local acceleration due to gravity. And as the satellites go past Greenland, they do a little dip and wobble. As they go through all the Earth, they're dipping and wobbling a little bit. They're not perfect ellipses. And someone figured out you can back calculate what the change in gravity would be as they circled year after year after year. And so that's what they did, and they were able to measure the change in gravity. It was so sensitive that over Greenland, you can actually see summer, winter, even though the ice sheet is 2 miles thick. It had a resolution of a few centimeters. It's a change in gravity of a few centimeters of ice. It's really very good. It was based on atomic clocks, by the way, that was measuring the distances using microwave frequencies. Of course, atomic clocks. Turns out there might be a better way of doing this, 100 times better. It's being considered by NASA. The graduate student, when he was my graduate student who did the experiment that tossed atoms up, come down, he also did an experiment that split atoms apart and put them back together again. And it's a good way of measuring gravity. And it turns out that a little set of lasers in a satellite might be 100 times better than the old way. And so now you only need 1 satellite. You don't need 2. Because you watch how these atoms drop in the satellite as it passes over Greenland and Antarctica. So it's amazing that that technology that just started in the late 1980s and 90s is actually finding its way into these applications because it was all based on frequency. Anyway, here's measurement of Antarctica. Where you see blue, you're losing ice. Very surprising. Scientists didn't expect Antarctica to be melting at all. Because Antarctica is very cold, global warming, more snow, comes in glaciers. Glaciers don't melt, you just get more snow. Okay. The last interglacial period, the last warm period, only 1 degree warmer than where we are today, only 2 degrees warmer since the beginning of the Industrial Revolution, and the climate goal of the UN agreement is to stay at 1 degree warmer, only 1 degree. We look back historically at the fossil record of what was the Earth like 1 degree warmer, and it turns out the sea level was 6 to 9 meters higher. Not 1 meter higher, 6 to 9 meters higher, just 1 degree warmer. We knew that, but we thought it would take 1,000 years, 2,000 years for it to happen. This satellite data is telling us that it might be done in a few hundred years. And in this century, you may go a few meters. But the whole thing is very scary because we also found out just recently that once this landslide of ice starts going into the ocean, it doesn't stop if you keep it the same temperature. It's like an avalanche. Once the avalanche starts, it doesn't stop. The only way to make it stop is to get colder. Okay, so even if you keep the same temperature, it's going. It's a good time of commitment. The higher the temperature, the more it runs off. There are some glaciers in Antarctica running off so fast, the speed is 4 kilometers a year. This is no longer your idea of a glacier. It's like a river of ice. Okay? Very, very scary. Okay. This is Shanghai and Pudong area. It goes underwater, all right? Lots of Hong Kong goes underwater, at least the low-lying parts. This is what Shanghai looks like today. And in the, that little town, Taichung, up there, that's where my father was born, Jiangsu province. And 1 degree warmer, this is what it looks like. Only where there's yellow is above water. Everything else is underwater. 10% of the world population is underwater. 1 degree warmer. Okay? Serious business. So I went to Department of Energy, and I started a new funding agency that wants to really make disruptive technology. So what's a technology? Well, this is an existing technology. As time goes on, it improves a little bit, and its cost and performance, and it's a horse and buggy. That's how people moved around in those days. And then when the Industrial Revolution came, and the invention of the steam engine, and then the steam locomotive that pulled trains, everybody, this was going great, and everybody said, that's great. Can you make a little steam engine to be a steam engine-powered car? And so someone invented that in 1789. It never took off because it was burning coal, and it was dirty, and you couldn't go very far, and someone had to keep the fire going, and everything else. Okay. So 100 years later, people invented the internal combustion engine, the gasoline engine, the diesel engine. And then what happened was a German by the name of Benz started a company, Benz Motorwagen, 1885, and by the turn of the century, by 1900, it was the most successful car company in the world, making high-quality cars, really good cars, and the motto was das Bestes oder nichts, the best or nothing. That was the attitude of Benz, which became Mercedes-Benz. You make really great cars or you don't make any cars. And they were making very good cars, but they cost a lot of money, so they were selling a few thousand a year. The dominant force in the automobile industry wasn't really an industry, it was a bunch of handmade cars for a bunch of rich people. Then someone else comes along, Henry Ford, and says, I want to make a car that's pretty good, not as good as Benz, but that every American who has a good job can own. And he introduced the Model T. He didn't invent the assembly line. He didn't invent the internal combustion engine. He didn't invent it. He put it all together, and he had a vision that he wanted a really inexpensive car. And that Model T, by 1910, I believe, or 1914, it really hit the market. By 1914, 1920, they were selling 1 million cars a year, not a few thousand. And that really changed transportation. That's a disruptive technology, okay? You have to get the price below a certain point. So the Tesla Model S is a wonderful car, and it costs $100,000. And so, you know, a few rich people can afford it. But if you can get something like a Tesla S for $20,000, everybody will want it. They won't even think about an internal combustion engine car because it would be so much easier to operate. So we call this Model T transformational. And so when I got to the Department of Energy, I founded a new funding agency to try to fund really crazy transformational things. Most of those things would not work, but some of them might work, and the ones that did work, we want them to work really big. So in America, in baseball language, we say that you're swinging for home runs. You're swinging for game-changing home runs. You're not trying to swing for just singles or infield singles. You want to make a big difference. Now, if you swing for home runs, you take a big swing, and you miss the ball a lot, but that's okay. But now most fund agencies don't want to fund things where you miss the ball a lot. They don't have the courage to do that. So we started this new funding agency and we had to get such good people that they could actually decide whether the idea might be good, because you can't decide by sending it out to referees, external groups. because the external groups many times don't recognize a really good new idea. It has to kind of work. And so, but really bright people who are used to actually inventing good ideas, and they don't have a much better chance of recognizing good ideas. So we got this quality of people. People in the National Academy of Sciences. I got one of my friends to lead it, who was elected in the National Academy of Sciences when he was in his middle 40s. But he was still in his middle 40s when he took the job. And a couple of others in their 40s when they National Academy of Science Engineering. Now, I have to say, I have to confess, I got elected in the National Academy of Sciences in my early 40s, but I wouldn't have worked for the government. Unless there was some other character who gets on the phone and says, I did this, why don't you come do this and join me? Because it takes that. And then once you get these really good people, you have to protect them from the rest of the institution. So we got really good people, and it worked. Now, at Berkeley, I told you, we started these solar fuels and solar energy projects. And while I was when I was Secretary of Energy, I actually started these so-called hubs. These are centers that don't fund a small company or individual professors or a group at a big company, but they want to get together a whole bunch of people, maybe under one roof, and really work on something in a concentrated way. And one of the hubs that I started was called, it was called JCAP. They called it JCAP, but it was sunlight to fuels, to transportation fuel. Now, I had the idea I wanted something like that, but as Secretary of Energy, you don't make the decision of who gets the money. That would be wrong in many respects. You might help, you and others can have the idea, but you have to hire good people and they make the decision. And so the decision was made, not by me. I didn't even know who they were thinking about, but it was a consortium between Caltech and Berkeley Lab. Just turned out. Those are the best. That was the best proposal. And Caltech got some money, outside donors to do this, Resnick, and Berkeley got a new building built, in part from outside donors. It was very, very unusual that a national laboratory actually gets private donors to build a building in a national laboratory. That's supposed to be government stuff. People give money to donations to build buildings at universities, but not national laboratories. So this was very, very unusual. I was Secretary of Energy, and then I became Stanford, and the person who took over my job says he was going to try to fundraise for this, and he raised some money from Jim Simons and his family, and they decided to name it Chu Hall. I didn't have anything to do with it, and nor did it. I'm poor, so I didn't have the money to, that was a $50 million building. I was very flattered by that because I wasn't even dead. Usually they name buildings after dead people. In any case, I did other things. There was a big, terrible tragedy, bad thing happened in the Gulf of Mexico. An deep shore oil well caught on fire. It was a BP oil well. And I had made a suggestion to the BP engineers, and they kind of laughed at it first, but then they decided, hey, maybe that's a good idea. Somehow, I didn't tell them. Maybe someone in the department told them, but the president found out about this. So after one cabinet meeting, he goes up to me and says, Chu, go down there and help them put that leak. Not the fire. By that time, the fire burned out, the ship had sank, and it was leaking oil. And so since late April of 2010, until July of 2010, oil and gas was gushing out of this thing 1 mile deep. Now, the letter says surface temperature during that summer, the surface of the Gulf of Mexico was 30 degrees centigrade, 86 degrees Fahrenheit. It was like a bathtub, very, very hot. The surface at the blowout prevention platform, the so-called BOP, it was 1 degree above freezing all year round. It's 1 mile deep. This is why we're in big trouble, because what we've already done to the climate, we have no idea what's going to happen. The delay time is going to be hundreds of years, or thousands of years. It's going to take thousands, or maybe 500 years or 300 years for the glaciers to melt. But the thing we've already done, we won't even get to the temperature because you have to warm up the ocean, and that's going to take hundreds of years. So this is a real problem. Now I'm going to go to Stanford. They're going to say time's up, so I'm not going to talk about anything I'm doing at Stanford. Oh, I'm going to talk about one thing. We can make diamonds. A postdoc of mine working, and we're working with another group, learned to make diamonds. These are diamonds. The thing on the right is the kind of diamonds he's learned how to make. That's 1 micron big. You can make them bigger, but the idea is to make them smaller. We can make them smaller, 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 smaller. We can make them really small, and they're single perfect crystals. For those of you who know about nanodiamond technology, there's nothing else like this. And we're doing other things in biology. I'm starting to collaborate with a professor, a brilliant young professor in Stanford Material Science, Yi Shui. We're trying to make better batteries, better batteries, better batteries. Those are the theoretical, those are what are considered the practical limits. But the first one here is where the technology is today. And so we're published a bunch of papers, got a couple patents, but the really big idea hasn't come along yet. And we're trying to make a battery, maybe silicon and lithium, but lithium and sulfur is known to be a very, very good chemistry, but no one could make a long-lasting battery that actually charges very quickly and lasts a long time. Very recently, we have maybe a new idea. It may work, it may not. 30% chance. But if it works, the battery can be 5 times better in energy density, how much energy, this big and this much weight, but it also can charge maybe 20 times faster. So we think that maybe you can go you can charge 100 miles, 150 miles in 5 minutes. This is very important because no one rarely travels more than 150 miles without going to the bathroom. So when you go to the bathroom, you're discharging, your battery's charging, and everything's all right. So that's the goal. That's the technical goal. And it's also it's cheap enough so you can get 20,000. You need many things. You need cost, you need fast charging, you need it to last a long time, and you need it to work at high temperatures without cooling. All those things. So we don't know we're going to do this. Air pollution. This is Beijing. Okay. The small particulate matter, PM 2.5, very, very deadly. More deadly than we knew just a few years ago. A new papers are coming out that says if you breathe air 10 micrograms per cubic meter, there's a 1.4 higher chance of getting lung cancer. That's pretty high, 40% higher chance at 10 micrograms per cubic meter. How bad is the air quality in Beijing? Average all year round, not just a bad day, 100 micrograms per cubic meter. Okay, here's a math lesson. How do you how do you go from 10 micrograms to 100 micrograms? You don't add 1.4 plus 1.4 10 times. You multiply it. Okay? Now, if you don't know that, you should study. And so it's as bad or worse than smoking a package of cigarettes a day, except everybody smokes. Amazing. Okay? Most of the filters don't get out this. The dust masks don't get it out. The air conditioning filters in buildings don't get it out. The National Academy of Sciences said in an air conditioned or air environment like that, they get out maybe half of it, maybe 10%. Okay? They get out the big stuff, and the air, it's cleaner, you feel better. But the deadliest stuff is the small stuff, and that's the thing hardest to filter out. So Yi Shui comes up to me and says, hey, I just discovered this amazing thing. If you take these polymers of its special type, you can actually trap some of these particles. And you know, the T55 means it transmits 55% of the light, and it gets 95% of the small particles out. So that means you can put on a dust mask and it doesn't get wet and soggy, or you can put it on a screen, or you can put it on a home filter, and later, then I told him, he told me about this, he published a paper on this, references down there, and so I said, yeah, I think I know how it works. Because he didn't know how it worked. And I said, well, what do you mean? I said, oh, here's how it works. See the charge rod? You can use it to pick up little pieces of paper. The pieces of paper are neutral. But the way it works is that charged rod creates an electric field, and this piece of paper, the charges, the negative charges are drawn a little bit closer to the positive charges, and these guys are a little bit further away. But because the electric field is stronger here than it is here, the paper goes to the rod. So that's how it works. That's the basic physics. Now, what happens if the charge is not positive? It's negative, like that. Then the same thing happens. The positive charges, on average, are a little bit closer to this than the negative charges. But because the electric field is stronger, the attractive force is a little bit stronger than the repulsive force, and the piece of paper goes to the rod. So I said, I think this is how it works. And once it hits the rod, the chemistry makes it stick. Okay? So now we've been doing experiments. We take these particles, smoke particles, and we pass them through a uniform field, and it gets rid of all the net charge, so only the neutral guys go through. It turns out not more than 95% of the neutral guys are neutral. And then we put them in this fiber, and they're caught. We take the charge off the fiber, it doesn't catch it. We change the charge of the fiber, the other side, and catches it. So, aha, looks like it works. So now that we know how it works, we're working to make the charge last a year and be very robust, even in moist climate like Hong Kong. Okay? Now, how did I know this? That's how I got the Nobel Prize. The focused laser beam that was the atom trop, it's light. But light is oscillating electric field. And the atoms would be drawn towards the place where the electric field is strongest. So it's kind of ironic that this worked like that, okay? So that was the fundamental idea of laser cooling, laser trapping. All right. Now, I know I'm gone way over, but it's okay. We started late, so therefore we're going to end even later. So when I talk to students and postdocs in my group, and I talk to members of the National Laboratory, where I was head of it for a few years, and even the employees at the Department of Energy, I reminded them, I said, the greater danger for most of us lies not in setting our aim too high and falling short, but in setting our aim too low and achieving our mark. I didn't say that. Michelangelo said that. Okay, now, I just want to end. I know it's late and you're going to sleep, but that's okay. This is a Nobel Prize ceremony in 1997. It was funny, I didn't know how big a deal it was. You think every scientist wants to get a Nobel Prize, and I knew scientists before they get the Nobel Prize and after the Nobel Prize, and they didn't suddenly get smart or smarter. They were clever. But once on the stage, when I started walking out, I said, this is a big deal. And so that's the ceremony, and that's me getting a Nobel Prize. And then after the Nobel Prize, there's a big banquet, and here they're serving dessert. And there at the center of the long white tables where the king and queen sit, and the Nobel laureates sit around in the center of the table. And there's a very important tradition in the Nobel Prize. The physicists are named first in the ceremony, and then the chemists, then medicine, physiology, and then finally literature, and peace is given in Norway. Now, why is that order? Physics, chemistry, medicine, physiology. Well, because it should be. No, seriously, the order is, that's the order that Nobel put his will. Okay, every time he wrote 5 wills. And so the physicists and their spouses get to sit next to royalty. That's one of the co-winners of the Nobel Prize, Bill Phillips, and he's there with the Queen of Sweden. Very gracious, lovely person. And you might think, is there a competition? How come he gets to sit next to the Queen and I didn't? Well, it's okay. I get to sit next to the Crown Princess. So it was a dirty job, but someone had to do it. Thank you. That's it.
Thank you, Professor Chu, for the inspiring talk. Please be seated in the front. I'm sure that there will be some questions on the floor. Please do not hesitate to raise questions, and a little souvenir will be given to you as a token of thanks.
Okay, may I now call upon Professor Xie, moderator of today's lecture, to be seated and host the question and answer section for us. Professor Xie, please.
So you guys can ask some questions, but I was given a very important question, so I have to ask that question first. But later, if you are willing to speak in front of the people, you can hold the mic and ask the question. If you're afraid, then I will give you a card, and you write down your question, and we'll read your question for you. Okay? But before that, let's ask one important question. I was given this question. So, Professor Chu, what can we teachers do to motivate and inspire our students to get interested in science and to improve our learning in science?
Well, what I found was if you learn science, especially the quantitative science, or engineering, so physics, chemistry, electrical engineering, computer science, those fields, mechanical engineering, you actually learn this mathematics, and once you have the mathematics, you can, and if you get a good education and you have self-confidence, and it's very important to have self-confidence. I talked about my terrible childhood. I didn't have self-confidence until I went to college. And then professors, were nice to me and patted me on the back and said it was okay. There. And you have this, you can teach yourself anything you want to learn. So if you learn something, then things change. And the information you got taught in school gets out of date. And the most successful people, not only in science and engineering, but actually in business and everything, they're actually learning all the time. And things change, and new things happen, new technology happens. And so the most successful people are able to keep track of these new things, and they're able to learn enough and teach themselves enough that they actually know about it and become new experts. So the last biology class I ever took was in the 9th grade. I think my biology work is as good as my physics work. Many of the people who study my group as physicists who turned into biologists have become very famous. And getting in national academies, things like that. So that ability to go from physics into biology, or polymer physics, or energy, I didn't know anything about energy, and now I'm into nanotechnology and I'm learning about batteries and nanoparticles, and it's just fun. I knew nothing about that, and now I have to learn chemistry because once we have these nanoparticles, we have to code them so that they behave right in biological systems, but there's not a reliable way to do this, and so there are papers published on it, but they're not reliable, and the people know that, and so we're trying to find out reliable ways of doing this. But I knew nothing about that 3 years ago, zero. I knew nothing about nanoparticle synthesis 3 years ago, or about how to make diamonds 3 years ago, nothing, okay? And so So it's like, energy when we were a bunch of other professors. Well, I don't know anything about energy. We'll teach ourselves. That is the most important thing you want to do. And if you have a rigorous science training in high school, even if you decide you don't want to end up in science, you can go elsewhere. And you can teach yourself other things. And you won't be afraid of it. Other people, they get afraid and say, oh, I don't know the mathematics, or I can't actually read these papers, or I can't actually understand the new technology. And that's a very big deal.
Okay. Thank you for the answer. Do we have any questions from the audience?
While you're thinking of questions, I have a comment. You, the high school students, you're allowed to laugh when someone makes a joke. Either that or I'm not that funny. These people sometimes laugh, okay? But you're too well behaved. Okay, I have two questions. I think maybe we should just talk about the first one. Can you tell us a little bit more about the Doppler effect in an atom? Okay, so I'm very, very quick. So this is frequency, and the atom responds to light with a certain probability that looks like that. And so if you're like this and you're parked at this frequency, and the atom is going towards you, it shifts. The atom sees the frequency not of the laser, but a little higher frequency. So if the probability of scattering a particle of light looks like this and you're over here, then the probability is over here. Okay? But if you're going the other way, the frequency shifts and the probability is less. So I hope that, the other thing is the atom has a very sharp frequency response. It's a very exact frequency light it likes to absorb or scatter. But it has that shape. All right?
Okay. It seems we have someone from the floor.
Testing. Greetings, Professor Ju. It is such an honor to raise a question to you. I have three little questions. Since you are the former Secretary of Energy, I want to ask, do you support the continuous development of nuclear energy? And the second question is, do you think that there's another alternative way to utilize nuclear energy so that it could be more efficient or more safety?
Yes.
The third question is, since nuclear energy may also bring the nuclear, may also call a way to produce nuclear weapon.
Yeah.
Do you support to spread nuclear energy, the use of nuclear energy to less, or I guess some countries like North Korea, so that they can use nuclear energy too? Thank you.
Okay, these are all very good questions. So let them take them in order. First, do I support nuclear energy? Yes, because of the following reason. Suppose you can't go to all wind or all solar energy. For example, Hong Kong doesn't have enough land for solar and doesn't have enough reliable wind. Neither does Japan, neither does Taiwan. There are many, many places in the world. Even the United States, where it has very, very good wind, very good solar, you can go 50% wind and solar, but you can't go 100% today. We don't have the technology. And so you still need energy to run industries. You still need energy for lighting and heat and everything else, and transportation. So what does it come from? If the wind stops blowing, the sun doesn't shine, well, if you could transmit the electricity all around the world, that's okay. But you can't do that. So, and we can't store energy. We can store it now for a few hours, maybe. It's going to go to a day in maybe 1 decade, of the utility scale. We can store energy, in a cell phone, but that only lasts 1 day, maybe half a day. But it doesn't last a year. And so we can't store electricity in batteries over a year or even a month. So we don't have good enough batteries, and that's not on the immediate horizon. So we need some sort. So it's going to be a mixture of fossil fuel and nuclear, or just fossil fuel. But if we use fossil fuel, we have to capture the SOx, the NOx, mercury, particulate matter. Okay, that particulate matter is going to cause a lot of cancer. Now, what Shenzhen did, I used to be, I mean, maybe 10 years ago, Hong Kong used to complain that all the dirty air was coming from Shenzhen. Right? And it's gotten much better. What they did is they moved their factories. But they're still polluting the air. And they're still throwing up carbon dioxide. And so that's still a problem. But that's what you first, you know, it used to be that the solution to pollution was dilution. Solution to pollution was dilution. But now there's so much pollution that you can't dilute anymore. And so I think in a world of 50, 60% renewable energy, you need power on demand, and then for that reason, nuclear should be part of it. So that's why I support nuclear. Can it be safer? Yes. The older generation nuclear reactors are being made safer today, and every time there's an accident, we learn about it. There's an accident, a serious accident, once every about 20 years. And Fukushima was the last one. Chernobyl was terrible. 3 Mile Island, it didn't actually contaminate, but it could have been an accident. And when I was Secretary of Energy, I was willing to help industry. I would partially fund them to help them design reactors. So if you lost complete control of the reactor, electricity, power, you couldn't control anything, water, they would never melt down, they would never contaminate. And it is possible to design reactors to do that. The next generation reactors. The current generation can be made safer and are being made safer. Finally, this business about, there's another thing, terrorism. Terrorists actually, you know, they like nuclear reactors because it makes a big deal. It's like when an airplane goes down, it's a big deal, okay? And so it's always a target. And so you have to guard against terrorists. And the terrorists will want to, you know, cause contamination or do something. They can't make a bomb, but they can cause contamination. The other thing is a nation state. Now, unfortunately, Korea knows how to make a bomb. Okay? And so that is unfortunate. Do we want to spread this technology that allows many other countries to make bombs? No. So one of the things that one would like to do is you still want to give, you know, developing countries want to have power, and if they could have, and if they don't have wind or solar resources, and you know, there's going to be limitations to fossil fuel, that could be an option. You know, right now nuclear is much more expensive than wind or solar. And so it's a very, very delicate thing, and how do you try to give them, and also to train them how to operate reactors safely. That's also very important. All those things are very important. And it's not a guarantee, but in the meantime, we also should work on cleaning up fossil fuel. Okay, so these are very challenging technical problems. And I hope some of you think of going into science and engineering, because we need young, brilliant people to solve these problems. You know, my generation is not going to solve all the problems, but if we don't solve the problems, the sea level will be much higher than 6 or 9 meters. But are you destined to be at least 6 or 9 meters? No. Because we can actually, we'll have 100 years or 200 years maybe to fix it. How do you fix it? You have to grab carbon dioxide out of the atmosphere and stick it on the ground. What's the best way of grabbing carbon dioxide out of the atmosphere? Grow food. Grow trees. Use a leftover rice straw or wheat straw or corn. Turn it into energy. Take the extra carbon dioxide from those plants and stick it underground. Then you're bringing carbon dioxide out of the air underground. And if you look at the numbers, it actually can be significant, really big, every year.
Thank you. Do we have time for one more question, or are we done? Okay, so any question from the audience? Yeah, I see. Okay.
Hi, Professor Chu. So I'd like to ask a bit more about laser cooling. As I've learned from my teacher that basically, because the atom sees the photon coming in a different frequency as in a higher energy, so it absorbs the photon, right? But then when it releases photons, it releases the higher energy. So it actually gives up a part of the kinetic energy itself. But the atom is not a person, so how does it perceive a photon as having higher energy, and why would it be willing to give up some kinetic energy when it releases another photon? Thank you.
Great. These are good questions, except the part about the atom not a person. I think they're people. No, I'm just okay, now you're beginning to laugh. This is better. Okay, so let's... actually, the question you asked is a very good question because it shows that you should be a scientist. Because many people, even including graduate students, don't ask that question. The people who were developing these things had to ask that question. How could it work? But go to the frame of reference. See, what happens, go to the frame of reference of the atom. Okay, and so what the atom does is it sees the light coming in, and it spits it out, scatters it in a different direction. Same frequency, right? Just bounces off. It's like a BB, and just bounces off at the same velocity. But if you take the atom and it's going towards this thing, and it has this little impulse, on average, teeny tiny little bit, the velocity gets a teeny tiny little bit slower. But there's another effect that's actually a much bigger effect. And it has to do with the disorder and order of the beams of light. Because the light comes in a very ordered way, and it goes out in a very disordered way. And so there's a subject called thermodynamics or statistical mechanics that actually says if you turn order into disorder, you can do things. You can do mechanical work. And then you can adjust it to cool it. So you probably don't understand it. I have to draw you a little picture to show you how it is. But now, so there are frequency shifts. It doesn't, the thing you said that if it absorbs a bluer light and emits the same bluer light, it's actually not exactly true. So then the thing, it is true in the frame of reference of the atom, but the atom is not moving as fast, okay? So it gets Doppler shifted. No? Okay, we'll talk about it later. This is good. She's good. Because if she doesn't understand, she sends signals that, okay, that's very good. Instead of just going like this and, okay, not doing anything. Okay, so the question is, how does an atom know what to do? How does it absorb it? How does it perceive to absorb this and give out that? I guess it's a paraphrase of your question. How does the atom know that it should absorb light at a higher frequency? Did I get that right? Oh, why would the atom release kinetic energy? Oh, it's because of actually the physics of it's shifting the light a little bit in frequency, and the entropy is doing it. So let me give you another example of let's see, analogy. If you take I'm just trying to think of analogies in terms of thermodynamics. But you're actually, see, let me put it this way. This is a good way. If you have an atom going at a certain force, and if it goes this way, it wants to slow down. If it goes that way, it wants to slow down, okay? Do you believe that? But if the atom is going a certain direction, the way the light is conspiring, it wants to slow down the speed of the atom, correct? Okay, so then it becomes just mechanics. If after all these hits and things, and the force is, the energy is force times distance, but the force is always on average, not always on each interaction, but on average, the force opposes the motion. Right? It's in the opposite direction. So think of this. you're trying to pull some object in water, okay, and this thing is moving around, right? And it wants to slow down. So it wants to slow down because every time if it's going this way, it wants to slow down, and it goes that way, it wants to slow down. So it wants to slow down because it's going in a certain direction, you're pushing opposite, so it's just Newton mechanics. The force is going in the opposite direction of the motion. It's always in the opposite direction, okay? Does that make sense? Okay, force, distance equals work, okay? But during that time when it's moving, and it's doing work, but it's doing work against its kinetic energy. Okay, so the fundamental thing is it's Newtonian mechanics. There's also some nice, cute thermodynamics, but we don't even need that. We can just use mechanics.
Thank you. Okay.
Being the sponsor of this event, your lecturing, your presentation maybe a little bit beyond the understanding of the young audience here. However, if you would let me use Olympic to equate to Nobel, if one of these audience today, being the Stephen Schooling in 20 years' time, you shall be proud of yourself to be here today. So thank you very much for coming.
Okay, and thank you, Leslie, for sponsoring this event and being so generous in every way possible. Thank you.
I think that's the time we have for the Q&A section. But before that, before we end this, let's thank Professor Chu again.
Thank you, Professor Chu and Professor Xie again. To express the college's appreciation, we have prepared souvenirs for both the speaker and the moderator. May I now call upon Professor Jimmy Yu, our college head, and Mr. Leslie Chung of the Philomathia Foundation to present the souvenirs. Professor Yu and Mr. Chung, please.
Firstly, to our distinguished visiting scholar, Professor Stephen Chu. Okay, thank you. And then to Professor Steve Xie, moderator of today's lecture. Thank you, Professor Yu and Mr. Zhong, and thank you, everyone.
On behalf of United College, we thank you again for attending today's lecture, and we wish you all a nice evening.
Thank you, and goodbye.